So at first you have these values, right? The mass of the empty calorimeter, the mass of the calorimeter in the room temp water, and then the mass of the calorimeter, room temp water, and hot water. And we're just going to use weighing by difference here to get these values, right? So I'm going to subtract this value from this one, and I'll have the mass of the room temp water, right? That makes sense?
Yes.
Here, I can make that bigger for you, Carson. I see you leaning into your.
Yeah, thank you.
Yeah.
Wait, so you said you subtract, the mass of empty calorimeter. Yeah, okay, I got that. Yeah.
Right. And then we're going to do the same thing here where we're going to subtract this value from this one in order to get the mass of the hot water. Right.
Right.
And then we've got these temperatures here. So if we go to the right up here, we're starting off right here because this is the heat capacity section, right?
Mhm.
With these two equations, which is essentially exactly what you just did on the quiz, Kevin.
Yes.
Right?
Yeah.
So you're going to have these mass of the hot water, mass of the room temp water. You've got sea water here, right? Do you guys know what that is?
The 4.184.
Yeah.
Yeah, 4.184 joules per degree Celsius times grams.
Mhm.
I believe the book uses the word specific heat to refer to that value. And then you got T final minus T initial, but these are different, right? T final is the same because we're talking about the mixture after we mixed them together, right?
Mhm.
But the initial temperature of the hot water and the initial temperature of the room temp water are different from each other, right?
Yes.
So you're going to plug those in and you're going to get these two heat values, right? Now let me ask you this, are they going to have the same sign? No, right? Because one of them is going to be releasing heat, one of them is going to be absorbing heat, and the sign is an indicator of the direction that the heat is going, right?
Mhm.
So in this case, the hot water is going to wind up being cooler, so its final temperature is going to be a lower value than its initial one. That means that this subtraction term here is going to be negative, and the whole term becomes negative, right? And then we have the reverse situation for the room temp water. So that's pretty straightforward. And then I go through this little derivation here about the heat of the calorimeter. So do any of you guys have any idea why we're calculating this value, what it's for?
Is that because the calorimeter doesn't it's what is it called? They said it was an enclosed system or didn't really
Yeah,
take
it's not a fully isolated system. The term that you might use is adiabatic, okay? In a fully adiabatic system, there's no heat exchange with anything outside the system, okay? But what's going to happen is not all the heat that's lost by the hot water is going to go into the cool water in this case. Some of it's going to go into the calorimeter, right? And if you have a decent calorimeter, it's going to be a small value, but it's still a value, right? It's still something. And it's going to wind up going into there. And what this is going to allow us to do is basically have a correction for that heat that's lost into the calorimeter that we can apply to each one of the following equations. Okay, so we can always account for that after this, right? Now I made up the data for you guys, and so I could have made it so that it was perfect without the correction. But in practice, it's very important. And last Tuesday, we just did this lab, and many of them got very low errors associated with it, according to when they compared it to the theoretical value they should have gotten. Without those corrections, though, that wouldn't have happened. Okay. So it's important that we do this. And what we're going to do is we're going to basically plug it into this equation here, right? So we just calculated Q hot. We calculated Q room temp. We know what the final temperature is, right? That's one of the values that we use to calculate Q hot and Q temp. We know the final, the temperature of the initial room temp thing. And so what this really should be is the temperature of the calorimeter, the way that it started off with. But we're going to assume that it was the same temperature as the room temp water that we put in there, which is a pretty fair assumption that we added it to the calorimeter and they were at the same temperature if we waited for a little bit, right?
Mhm.
And it also just keeps things from getting really gross with our equations, right? So you're going to plug that in here. So we just talked about Q hot's going to be a negative, right? Q room temp's going to be a positive. Some of the heat is going to not go to Q room temp, right? So this is going to be less positive than this is negative, right? The magnitude of Q hot is going to be higher than the magnitude of Q room temp, which means that when we add them together, we're going to get a negative. All right. The T final is higher than the initial room temp water. So this is going to be a positive. This whole ratio on the inside, therefore, comes out negative. So we have to multiply it by this negative out here to make sure that our CP value is positive, because CP should be a positive value. Does that make sense?
Yes.
Okay. And that's part one. So then I start to go into this little derivation here for something I'm calling Q process, right? And I'm being a little ambiguous about what this heat is because what we're doing here, they're not always reactions, right? We're doing some reactions, but like say part 4 where we add the metal in there, that's not a reaction, but they're all some kind of process, all right? And what I'm saying is that Q process plus the heat exchange of the water plus the heat that goes into the calorimeter, this is all going to equal 0. And what that assumption is that outside of the calorimeter, there's no heat lost outside of the calorimeter. Okay. And then I go through a little derivation here, and then I come down to this equation right here. And this is really your important one. Okay. This is the one that you're going to use to solve all the next 3 sections here. Okay. So we get to this guy right here. Let's look at part 2 here. So we have a mass of the calorimeter plus water. We need to know the mass of the water in this case, right? So how are we going to get that? We're going to subtract the mass of the empty calorimeter. We're going to go back to this value from part 1 in the next couple parts. All right. So then we'll have the mass of the water. Let me make this bigger for you guys. Then we'll have the mass of the water. We have the mass of the ammonium chloride that we added. We have the initial temperature of the water, and we have the final temperature of the water. What's going to happen when I put the water in the calorimeter and I add the ammonium chloride? What do you guys think is going to happen? We saw this back when we were looking at properties, chemical and physical properties with the ammonium nitrate. We added it to the water. It got cold. It got cold when we did that, right? So we're talking about an endothermic reaction here. So we're going to come in here. We're going to go to our Q process. We're going to put in that mass of water. We've got our C water here for the 4.184. We've got the CP value that we calculated above, right? And then we've got our T final minus T initial, which are pretty clear here, okay? We're going to make sure that we apply this negative sign here to Q process so that we get the right sign for the whole thing, right? Because this should be a negative or a positive thing if it's endothermic, the way we're defining it.
Negative.
No, good guess. It should be positive.
Positive.
Positive, yes. Okay. So we're going to have that positive thing there. All right. The next thing I ask you in the questions is what should, so we're going to have this value. The next thing I ask is what should the value that we got have been? Okay. And that's a question I could have just left all the way up to you guys, but I'm a nicer person than that. So what I said is we're going to use this formula right here. There's a couple of ways that we could have calculated this, but we're going to use this guy right here, equation 9. All right. And then I went ahead and did it for you. All right. So equation 9 involves the standard enthalpies of formation. Okay. These are well-known values. There's a table in your book. I believe it is repeated in the appendix as well. And there's different ones for different things. So if this is our equation, I need to know the standard enthalpy of formation of ammonium chloride, ammonium ions that are aqueous, and chlorine ions that are aqueous. Okay. And I just went and looked them up, right? So here, this one would be the one for, I believe, ammonia. This one here is the one for chlorine. Okay. I'm summing them together. That's what this term right here means. Okay. It looks like I'm subtracting them because they were both negative to begin with. Okay. I skipped the part where I resolved that negative sign there. I'm subtracting from that the standard enthalpy of formation for ammonium chloride because that is our reactant. And I get 15.7 kilojoules per mole. Okay. Now, we now have a handle for figuring out the heat that's going to be absorbed for all reactions. Okay. We now have to apply it to our specific reaction. And to do that, we need to know how many moles of ammonium chloride we dissolved. Right? How are we going to go about doing that? Okay, so we know the mass of ammonium chloride that we have, right? So what do? We go and figure out the formula mass of ammonium chloride, right? Where we add up the value of nitrogen and hydrogen and chlorine from the periodic table, right? And we decide that it's 53.491 grams per mole. And then we go ahead and, I mean, ultimately we're dividing the mass that we had by that value, right? We can see our grams canceling. Now we know how many moles we had if we started off with exactly 5 grams. You guys don't, right? But if we had exactly 5 grams, we would know how many moles of ammonium chloride we'd had. We know that this reaction releases 15.7 kilojoules for every mole. I can go ahead and multiply those two together. I see that I got my moles canceling here, and I get 1.47 kilojoules for that reaction. Right? You guys following how you do that? Yes. Okay. All right. Let's see here. So what you guys are going to do is you guys are going to input the exact mass that you had, right? That you guys used over here, and you're going to figure out your own theoretical value, right? Yours isn't going to be exactly 1.47. You need to calculate it for the 5.350 grams that you had. Okay, does that make sense? I hope so. Jamie gave me a thumbs up. Look at this. I love the feedback. You guys are so quiet. All right. After that, we're going to calculate a percent error. Do you guys know how to calculate percent error now? Because you should. Right? We've done that a couple of times already. We've got we got an actual value that we measured. We've got a theoretical value. We're going to take the actual value minus the theoretical value. We're going to take an absolute value there so that that's a positive. If it happens to be negative, we divide it by the theoretical value. We multiply it by 100%. I spelled it out very clearly the first time with our first lab in the measurement lab. And you guys can go back and review that if you're at all confused. Okay. So we have that. Then we got part 3 here. We're given a concentration of HCl. We're given a concentration of sodium hydroxide. We're getting volumes for both of these. Okay. Now let me ask you guys this. After thinking about the limiting reagents lab that we did last week, what do you think I'm getting at when I give you these concentrations and these volumes? What do you think we're going to have to calculate from that? Anybody?
Enthalpy.
Yeah, we are. We are, right? But directly, what did we calculate last week when we had the concentrations and the volumes? We calculated the moles, right? Because molarity is moles per liter. And that's what we were doing. So that's where that plays in, okay? This does not play in to the heat equations, okay? Because in the heat equations, we're talking about mass, right? And we measured the mass directly. So let's keep going here. We got the initial temperature of the HCl. We're going to assume that both the HCl and the sodium hydroxide had the same initial temperature because that's easier. Then we have the final temp of the reaction mixture, and then we're given the mass of the calorimeter in the reaction mixture. Okay. So when I say reaction mixture, I mean the mass of the HCl plus the mass of the sodium hydroxide. Okay. Obviously, we're going to subtract out the mass of the calorimeter, and that's going to give us what that mass should be there. Okay. Then we're going to go back up to Q process here, and we're going to plug in these values, right? We got an initial temperature of the HCl. We've got the final temperature of the reaction mixture. We've got our CP value. We know what our CW is. We're also making the assumption here that the specific heat is not different from water of these two solutions. Again, because that's convenient for us. It would get a little dicey otherwise. But it was a pretty valid little assumption we're making there. And then we have the mass of the water, which in this case is going to be the mass of our reaction mixture. We plug it all in, we get our Q process. Sam, do you think this is going to be a negative or a positive Q process?
Sorry, I have kids distracting me.
Okay.
So I was just dealing with one of those.
All right, all right. Well, if the endothermic one is positive, and this one is going to get hot, so it's going to be exothermic. Given that, does anybody think that they know what Q process is going to be, if it's going to be positive or negative?
It's going to be negative.
It's going to be negative. That's right, Annalie. Yes. All right. So we're going to get a negative Q process for that, but we're not going to let that sway us. Okay. And then the next thing we need to know is what would the theoretical one be, right? Again, I was super nice about it and I worked it all out for you. Okay. So we have this whole reaction up here. I say, we don't need all these spectator ions because that's going to make this kind of gross. Let's get rid of those. And let's look at just the pertinent reaction that we need to worry about right here. Okay. I calculate out. Now notice this now becomes generic for all acid-base reactions, right? This is any areneous acid and any areneous base now, we can figure it out, which is pretty powerful, actually. That's kind of cool. Okay. And the reason for that is because that's the only bond that's forming here, right? Because we wind up with having all of these ions in solution. And then most of the metal and the counter anion here, they remain in solution. Okay. So any like potassium hydroxide with sulfuric acid, nitric acid with sodium hydroxide, there's any of those areneous acid base pairs, we can use this to figure out how much heat is going to get evolved from that, which is kind of cool. And it's also not entirely true. It's only true when you have dilute solutions, okay? Because otherwise you wind up with something called the heat of solvation, which just has to do from just like dissolving things, just like we saw with the ammonium chloride. That'll start to play in if you start to have more concentrated acids and bases that you mix together. You can actually mix together, like, say, concentrated sodium hydroxide and concentrated sulfuric acid together, and it'll create so much heat, it'll start to boil all by itself. Which can be fun, I plugged it back into this equation up here after I looked up their values. And I see that I'm getting negative 55.8 kilojoules per mole for this one. Okay. Now what I need to do is I need to find my limiting reagent again. Okay, just like we did last week. So I need to take the concentration of HCl, multiply it by the volume of HCl in liters to find those moles. And I need to take the concentration of sodium hydroxide and multiply it by the volume of sodium hydroxide in liters so that I can find the moles of sodium hydroxide. Whichever of those two values is lowest is going to be my limiting reagent. Okay. So then I'm going to have the moles of my limiting reagent, and I'm going to multiply it by that value that I just found, that negative 55.8 kilojoules, and it will tell me how many kilojoules of heat were released by the neutralization of those two acids. Okay. So we got that. I like how these labs are kind of leading one into each other. We're using the skills from the last one in the new one. I'm going to pat myself on the back for that. Now we have the specific heat of the metal. All right. Now for this one, we're doing something a little bit different. Okay. Now what we're doing, and I think this is actually pretty clever, is we actually want to calculate this C value, the specific heat, for the metals that we have, which is kind of cool because the specific heat is specific, even though that's not the reason it's called specific, but it's specific and unique to the different metals. Okay. So we can take an unknown metal and then heat it up, add it to some water, and by measuring how much water we had and how much it heats up after that, we can identify that unknown metal, which is kind of nifty if you think about it. So what we're going to do now, and this, a few people got a little confused about this, okay, is we're not calculating a new Q process, okay? We're going to come up here and we're going to use the same formula that we used before for Q process, okay? And we have all the information here, okay? We've got our mass of water, we've got the initial temp of the water, and we've got the final temp of the water and metal here, okay? So we have all of the information that we need. Whoop. I lost my... We have all the information that we need to calculate out our Q process again for this one. All right. But what we're going to identify is that this Q process here is equal to the heat that was released by the metal. Okay. So Q process equals Q metal. And if it equals Q metal, even though we found it by a different means, that means that it also equals the mass of the metal times its specific heat times its change in temperature. Okay. And if that's true, and we know the final temperature of the metal, because it was the same as the final temperature of the water in the metal, and we know the initial temperature of the metal, all right, and we know the mass of the metal, then we can solve for the specific heat of the metal. All right, and we can take this Q process here, and we can solve for it right here. Okay. We're going to see that this Q process is going to be a negative value, right? But this is also a negative value right here. So these two negatives are going to cancel each other out. We're going to get a positive specific heat for that metal. Now, once we have that, what we're going to do is we're going to go down a little bit more. We're going to look at this table. And we're going to say, okay, which one of these specific heats is it closest to, right? And then we're going to identify which metal we had. And you guys are at a slight disadvantage from the hybrid students in this case because you don't get to see the metal, but you have the advantage of the fact that I made sure that the numbers work out really nicely for you. And it's going to be close to one of them.